So first of all, the only trig derivatives we have learned are sine and cosine. So for figuring out the derivative of tan, we can do a preliminary change since we know that tan is equal to sine over cos. We can do that, and now we just have a quotient rule. Quotient rule says which one do we keep the same? Top or bottom? Bottom. Keep the bottom the same. Times by the derivative of the top, and the derivative of sine is positive cos. Again, I always think about the graph of sine, I'm like, because it gets worse. Because when we have to work backwards, we have to rememorize the positives and negatives. So the derivative of sine is cos, and then minus, keep the top the same. The derivative of the bottom, well, that'll be negative sine over the bottom squared. Then I can write it in brackets there, or I could put the squared in between. But for now, I'll just write it in brackets. On the top, can you see that the top will be cos squared plus sine squared? And again, from grade 12 pre-calculus, that's one of the formulas you learned, that no matter what the angle, sine squared plus cos squared is always equal to 1. So the top becomes 1. The bottom is cos squared. Cos is the reciprocal of secant, so we have shown that, I guess notation-wise I should have paid attention and used dy dx instead of y prime, but we'll just say it's okay for today. And this is another one that we will be able to say, you know how in your identities unit in grade 12, certain things you were allowed to use for proofs? There are certain derivative rules you're going to be allowed to use, like the derivative of sine is cos. You're going to be able to use the derivative of tan is secant squared. Can you work backwards? Would it be positive or would it be negative? You went backwards from a negative sign. Would have to be positive cos. And then the minus 2x, working backwards, it would have had to originally have been a minus x squared. And of course, there could have been a number there. So if you have a favorite number that you like to add to questions, right? Number 3 is lucky, perfect. Add the number 3. But you don't have to have a number there. I better erase it, because inevitably someone will say, why does it have to be a 3 if I put a 3 there? It can be any number. Same thing working backwards on this one. This one would stay negative. Because the derivative of sine is positive cos, so having that negative 3 out in front won't change. And yes, so now we are allowed to use that the derivative of tan is secant squared, or you could write it as 1 over cos squared, which means we add another thing into quotient rule, chain rule, product rule, and another rule that you've got to keep strict. So what does that look like? You look at an equation and you have to decide what kind of rule is present here before I take the derivative. So we're always analyzing the equation first. In this one, I have one thing, x squared plus 1, multiplied by tan x, so we have a product rule. Product rule says, keep one the same, times by derivative of the second one. plus, keep the second one the same, times by the derivative of the first one. And for the most part, on tests and stuff, if I ask you for the derivative, you do not need to, you can leave it like this. Perfect. If it's a show that question, then you're going to have to manipulate. So again, when you're in your textbook, it's good practice. Look at the answer key. I've already noticed your algebra skills getting better and better from doing that. That's going to be a huge help for you in university. The stronger your basic skills, and what we're doing in calculus is not basic algebra, like it's advanced algebra skills. But the stronger that you have that going into your university classes, well, the better you're going to be. And the less stressful it's going to be. So probably what I would do on this one, and take some time, well, if I have a fraction, I could do the quotient rule, but if I have a fraction with just a number on the top, I tend to prefer to move that to the top to a -1. I find the chain rule a little bit less cumbersome than the quotient rule. Seems like it's a bigger thing. And especially with just a 1 on the top, if you did the quotient rule, when you have to do the derivative of 1, you get a 0, just sort of messes things up. So this will make it a little bit cleaner. Inside of tan is 2x. How do we know we have to use the chain rule? Is if the inside function has its own derivative. So the derivative of 2x is 2. Yes, we have to use a chain rule. So now, for our derivative, our outside function is tan. The derivative of tan is secant squared. And we keep the inside the same, multiplied by the derivative of the inside. Plus another chain rule. But this time, tan of x is inside of the -1. So the derivative of the power of -1 would mean the -1 would come out in front, subtract 1 from the exponent, keep the inside the same, multiply by the derivative of the inside, and again, wouldn't need to factor this, wouldn't need to simplify. Something I do want to point out, secant squared 2x and secant squared x are different. So you wouldn't be able to be like, oh, can I factor out a secant squared of something because I have that? No, they're different. In order for a factor to be the same, it has to have the same function, the same variables, all the way through. So again, analyze the question, prepare yourself, think of all the rules that are going to have to take place to find y prime here. Do you notice that you have a y squared? So that's going to be implicit differentiation. You notice the 7x is inside the tan, so that is going to be a chain rule. So first of all, we're going to take the derivative of the whole thing. So in implicit differentiation, if you don't want to write this step, that's perfectly fine. We're taking the derivative of the whole thing. What does that mean when you have a y? Well, you deal with the derivative of y just like normal, so derivative of y squared would be 2y, but then, and I like to use Leibniz notation in this, just to not get it confused with y to the -1 or something like that, or y to the 1. Equals, and on this side it's the chain rule, outside function is tan. Derivative of tan is secant squared, keep the inside the same, multiplied by the derivative of the inside. So then dy dx or y prime, and maybe because the question wrote y prime, maybe I'll write y prime at this moment, just so that it matches with the question. I have 7 secant squared of 7x divided by 2y. Okay, so the next 3, I'm going to get you to try on your own. All right, I'll put up the answer. First one, sine of x was inside of tan of x, so you've got to be careful that you don't think of this as a product rule, noticing that the sine is inside of tan, not multiplied by tan. I would change it to a -5 because I just have a number on front. If you did the quotient rule, perfectly fine. This one has a double chain rule because the sine is inside the -5 and the 6 is inside the sine. So if we walk it through, what do I do first? Derivative of my outside function, though, -5 comes out in front, I subtract 1 from the exponent, and I keep the inside the same. Then I multiply by the derivative of the inside, and the derivative of the inside is another chain rule. My outside function is sine, so the derivative of sine is cos. I keep the inside the same, 6x, and then multiply by the derivative of the inside function. Oh, we could make a chain rule with like 7 things inside of each other and just keep going and going and going. And by the looks of it, I might be the only one who really enjoys that. There it is, chain rule twice. All right, outside function was the 3. So the 3 would come out in front, subtract 1 from the exponent. Again, if you want to put tan x in brackets and have the squared on the outside because it's easier to visualize, that's fine. So now we get back to a question we've done before, which says find the equation of the tangent. So the tangent is a straight line. We'll have to use y equals mx plus b. And in order to find that equation, we need 2 things. We need the slope, and we need a point. The point is already given to us at the origin. We need to find the slope. Well, again, after doing so many complicated derivatives, I find that if you do enough complicated derivatives, you forget what a derivative actually was. So we have to review. What is a derivative? A derivative is just an equation to find any slope of any tangent. So if I have sine x, I can find the derivative. The derivative will be cos x. And at x equals 0, we can use our unit circle. Right? How was that for mental? Did you remember that cos of 0 was 1? Right? Think of our unit circle. A little circle. Here is when the angle is 0. The coordinate is easy. Because the radius is 1, it's 1 to the right, so it'll be 1, 0. And we have to remember that on our unit circle, cos was the x coordinate. There's a review of your unit circle. Please have it memorized again in your next class. But you do have to know your unit circle again, so we'll keep reviewing. If you know If you know all of the answers in quadrant 1, oh, this is, okay, so here are pi over 6 family, the pi over 4 family, and the pi over 3 family. For the coordinates of these, as a shortcut, I like to use counting. If you start with 0 on your y-coordinate, your next y-coordinate has a 1, 1 over 2. Your next y-coordinate has a 2, root 2 over 2. And your last y-coordinate has a 3, root 3 over 2. It works backwards. If you go from this 0 to this one, 0, 1, 2, 3. And it's also, if you draw it mostly to scale, it's also going to be easy to see that at the green point, it cuts the y perfectly in half. At the purple point, it cuts the x-axis perfectly in half. More so, I guess the idea is, does the purple cut the x in half, or is it more likely that the purple cut the y in half? Well, it's more likely that it cut the x in half. And so you have that my x-coordinate is a half for the purple. So there's, look at that. Nice little review of our unit circle. We found our derivative. We found our slope was 1. We now can type that into y equals mx plus b. Pretty easy to figure out that b is 0. So the equation is just y equals x. And I don't know if you remember when I pulled up that visual of the tangent line on the sine graph, our very first tangent was exactly at y equals x. You guys ready to go down some more rabbit holes? It's coming. Okay, another one for you to try. You can try the next two. All right, let's check how you did. So first of all, we would have a chain rule with the sine 3. And sometimes, I will tell you that sometimes it is really helpful to rewrite that with brackets like that. Then it's really obvious what's the outside function and what's the inside function. So the 3 would come out in front, making a 6. Keep the inside the same. Subtract 1 from the exponent, making it squared. And then you have to multiply by the inside function, which is a cos. And then minus 3 cos x. So at this point in our question, we have done the derivative. And in a show that question, I would then look at what is coming up next. I need to show this as all one thing. In an idea right here, this is one thing with two major things multiplied by each other. A cos 2x. You could even put the minus 3 as its own thing and have 3 things multiplied together, but we need to sort of get a visual of what is happening here. Now, with that in mind, seeing that one of the factors has to be a negative 3 cos x, and seeing that I have a negative 3 cos x here, and a cos x here, and a 6 here, as far as common factors go, there's a cos x in common, and there's a 3 in common. But because I looked at the show that, and also saw the negative out there, instead of, like normally I would say, if you were factoring this, you should take a 3 and a cos x, because that's what's in common. But anytime you want, you're allowed to take out a negative. So why not take the negative 3 cos x, because it matches up with what was in our final answer. Now, because of that, I'm left with negative 2 sine squared x plus 1. This needs to equal cos 2x. And I don't know if there's ever been a stronger hint to look at one of your identities from last year than that. Do I have a cos 2x formula? And they're up here on the wall, which is equal to 1 minus 2 sine squared? Yes. So because that matches up perfectly with the formula that we have from grade 12, we can just exchange it right away. Your arm was all hidden under your hair. I was like, it looked like it was gone. Temporary. That's on the video too. Derivative of the outside function. Again, you could write the tan 2x all in brackets with a 3 on the outside of it. Perfectly fine. Then the inside function is the tan 2x. The derivative of tan 2x is another chain rule. Outside function is the tan. So that would be secant squared, keep the inside the same. And then derivative of the inside again would be 2. The rabbit hole continues. Oh, if we had a derivative for sine, cos, and tan, shouldn't we be able to do the reciprocals? Yes. And these are the most common forms of the derivatives of the reciprocals. Okay? Personally, I have to refigure them out every single time. Because I'm like, oh, I didn't remember it. Because I use this even less than finding the derivative of tan in my day-to-day life. So what I would do is if I was trying to find the derivative of cosecant, I would change it to 1 over sine, which well, I'll write it like this. Is just a sine to the negative 1, which is a chain rule for sine. And so because I can do that, I bring the negative 1 on in front, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. And this would give me negative cos x over sine squared. If I wanted to rearrange that, I could rearrange that by having a negative. I could have a 1 over sine x and a cos x over sine x. So I would get a negative cosecant x cotangent x. So if I had the derivative of cosecant and I didn't want to remember this and do it directly, I could do it indirectly by changing it to sine. Same thing, secant, you could change it to 1 over cos and do it in a different way. If you had left your derivative like this, as negative 1 sine x to the negative 2 cos x, that's perfectly fine. It means the same thing. And same thing with cotangent x, you could change it to tan to the negative 1 and deal with that. But if you wanted actual formulas for these, this is what it would look like. Something that I find interesting with the derivatives is, do you remember these identities? Sine squared plus cos squared equals 1, tan squared plus 1 equals secant squared, cotangent squared plus 1 equals cosecant squared. So you have that cosecant and cotangent go together, and they go together in the derivative. And you have that secant squared and tan squared go together, and secant and tan go together in their derivatives. I think it's just pure coincidence, but it could be, if you did decide that you wanted to have these memorized, that could be helpful. Okay, so try using those new formulas. Try this one. Oh, okay. All right. So using the formulas, you could do this directly and get those answers. If you did it by changing it to sine and cos, you would have got a different answer. That would be equivalent. And there's some practice questions. And a very fun chain rule if you want to try it. It has all 6 trig functions. How much nicer could that be?